Hello, everybody. Here we continue our journey into understanding the properties of the stars. In this video, we're actually going to take a lot of the knowledge that we've been building up over this entire semester and put it together to get after the size of the stars themselves. Seems kind of ridiculous that we can just make a couple of observations and be able to determine how large a star is, but we can do it. All right, let's go ahead and start by taking a look and appreciating the vast variety of sizes from the smallest to the very largest stars that are out there. And for this, I'm going to show a video that's on YouTube. I'll put a link that you can see in the weekly README. This is a size comparison of the stars. So what we're looking at now are actually neutron stars. We'll get there eventually in this semester. They are the dead remnant cores of high mass stars. This right here, Sirius B, is what we call a white dwarf star. Again, we'll get there. This is the core of a dead star like our sun. It's where our sun will eventually end up whenever it dies. Black dwarfs are theoretical. They don't exist in nature yet. You think that might be the sun, but no, we're not there yet. There's TRAPPIST-1. There are 7 terrestrial planets in orbit around that star. Those are what we call red dwarf stars. We're getting a little bit larger in size, but now we're finally up to the size of the sun. Alpha Centauri, a nearby star, which also has a habitable Earth in orbit around it. Starting to get a little bit bigger. Yes, some stars are binary stars, and yes, sometimes they do touch one another. Now we're getting ridiculously large. We're already up to the star Arcturus in the sky, what we might want to call a red giant, although we're about to see that calling it a giant is a little bit of a misnomer since there are even gianter stars out there. There's our North Star, Polaris, much, much bigger than our sun. There's Aldebaran, sometimes called a orange giant star. And now you can see that they've put the orbit of Mercury down here for reference. So yes, the surface of that star would be all the way out and encompass Mercury if it was in our solar system. There's Rigel in the constellation Orion, the bright star in Orion. There's one of the phases our sun will end up in its red giant phase as it's going through its death throes. There's the star Antares. It's not Mars. Getting even larger. This is kind of ridiculous. These stars are incredibly large. And notice that it's trying to show you the color of these stars. Betelgeuse is a red giant star, one of the largest stars out there. Notice that's Jupiter's orbit for reference. And here's one of the largest known stars that's out there, UY Scuti. And this video even tries to display the theoretical limit of how big stars can be. And now it's just going to quickly show us a summary of all the sizes of the stars. There's the sun. So, as you can see, stars come in a lot of different sizes. And let's just go ahead and give some generic terminology. We're going to build on this as we move forward through the coming weeks. But just in general, we can kind of break down stars into 2 broad categories, what we call the giants and the dwarfs. Giant stars are stars that have radii that are 10 to 100 times larger than the sun. So they're the stars that are much, much bigger than the sun. And since they're so much bigger, we call them giants. I mean, astronomers are not known for being the most creative namers out there, but we also have supergiants and hypergiants. Those are the ones that can get ridiculously large, like 1,000 times larger than our sun. We saw that one stretches all the way out to the orbit of Jupiter. So stars can get incredibly large. But in general, we have giants. And to give you some examples, so O and B type stars, we would simply call those blue giant stars. They can get more gianty and be blue still, but these 2 stars, O and B type stars, are blue giant stars. Then we have some dying stars, stars that are in their death throes on their ways to ending their lives. And we have things like Antares, misspelled, sorry about that, and Betelgeuse, which are absolutely enormous stars. They're cool, they have cool surface temperatures, so they're red in color. So if they're giant and red in color, we call them red giants. Nailed it. And then we have dwarfs. And dwarfs are stars that are comparable to the size of the sun and smaller. So the sun is technically what we'd refer to as a dwarf star. We would call it a yellow dwarf. And then we have, say, our M stars, our coolest spectral class of stars. We would call these red dwarf stars. K stars, we might call orange dwarfs. So we have giants and dwarfs. Not adding a whole lot to our knowledge base right here. I mean, it's really, really interesting, and I absolutely love seeing those videos of the size comparisons of stars. It's mind blowing to see the huge variety of sizes, from the absolutely enormous to the much smaller than you'd expect stars that are out there. But still, how do we go about determining the size of these stars? You can't physically see the size of the stars, except for a few of them. We actually can measure the angular size of Betelgeuse using telescopes like the VLT, but that's only in the past couple of years we've been able to do that. For the most part, with a telescope, there's just a point of light, and that point would be the size of the diffraction limited angular resolution of the telescope if you're observing from space. So how do we actually determine the physical size of a star? This is a big problem. And the solution is actually pretty simple and something that we're already prepared for, and we spent a lot of time on already. So how do we determine the size of the stars? And really, we just have to use Stefan-Boltzmann, the astronomer's version of the Stefan-Boltzmann's law. So if you remember that the Stefan-Boltzmann's law said that the radiative flux is proportional to the temperature to the fourth power. You don't have to memorize these equations. The one that you need to know is going to be highlighted in blue. You can see where we're building towards what's called the luminosity radius temperature relationship down there at the bottom of the screen. But I want to walk you through how we actually determine the size of the stars, because it interconnects so much of the knowledge that we've worked so hard to understand. And it would just be a shame to hide all of that and to from you and not show you and let you actually glory in the fact of everything that you've worked towards this semester. So we have the radiative flux, the amount of energy per second per square meter that a star gives off is proportional to the temperature to the fourth power. The actual equation is sigma, just a number, the Stefan-Boltzmann constant, times temperature to the fourth power. And really, radiative flux is just the luminosity, the amount of energy per second, the watts per square meter surface of the star. So we know about the luminosity quite a bit. We spent a long time talking about luminosity of stars. The surface area of a star, I mean, it's just a spherical shape, so it's the surface area of a sphere. I can work with those two things. I really understand those. So let's play around with those. Well, what is the surface area of a sphere? Stars are roughly spherical in shape, very close to spheres. So at this surface, the photosphere, that's how we measure the size of the star. What we're after is the radius, how far from the center of the star to the photosphere. So the surface area of a star equals 4 pi times the radius squared. It's the surface area of a sphere. If you don't remember that geometrical equation, it's a standard equation of geometry. 4 pi r squared is the surface area of a sphere. Okay, so now notice that I've already gotten to the radius of the star. I have the area, and the area depends on the radius. I'm already getting to the radius. So now we could go ahead and go up here. Luminosity divided by area equals sigma t to the fourth. That would be luminosity just multiplied by area on both sides. So you get the luminosity equals sigma times the area of the star times the temperature to the fourth power. But I know the area, the surface area, is 4 pi r squared, where r is the radius of the star. So the luminosity of a star equals a whole bunch of numbers multiplied together. 4, that's an easy one. Pi, we know about pi. And sigma, new, but still just a number. So just a number times the radius of the star squared times the temperature, surface temperature of the star raised to the fourth power. We can simplify this quite a bit, and I'll show you how this all works out on the next slide. If we put this all in solar units, so we'll solve for the luminosity of the star and number of solar units. And we'll input the radius of the star in solar radii and the temperature of the star in solar temperatures. And we have a really, really simple equation that the luminosity of a star equals its radius squared times its temperature to the fourth power. Not that bad. We call this the luminosity radius temperature relationship because we're good at naming things. Notice, so far, we have been working towards where we can determine the temperature of the stars in a number of ways. We can use photometry, photometric measurements, measure, say, the apparent and absolute magnitude, use stellar parallax to determine the distance, and that gives us the luminosity of the star. Apparent brightness, apparent magnitude, plus the distance gives us the absolute magnitude, which gives us the luminosity. So we can measure these two, which allows us for a way to calculate the radius. And this is how we go about determining the sizes of the stars. Through observations, we determine the luminosity and the temperature, which allows us to solve for the radius. And we know we can use all this because the radius of a star is nice and stable thanks to hydrostatic equilibrium. Man, so nice whenever a plan comes together and everything comes and can be put into this nice logical package. Okay, so this is what you need to remember. Notice that these are the ones that are in blue. We have the luminosity radius temperature relationship. However, since we measure the luminosity and we measure the temperature via observation, and we want to figure out the radius, typically this is shown as the radius luminosity temperature relationship. I just shuffled the words around there. I'm not really, as long as those three words are there, I don't really care what order you put them in, as long as you can recognize that those three words with the word relationship after them is referring to this. I'm a happy professor. But this is the more practical way, where the radius equals, and I could just solve for the radius, the square root of the luminosity divided by the temperature squared. And this is going to be one of those equations where you will just have to plug in some numbers, especially with the homework. But it's really, I give you the numbers, you plug them in, you get the answer. One of the few times I actually just have you plug in numbers to an equation. But note that these have to be in solar units. And remember that one solar luminosity is the luminosity of the sun, 3.828 times 10 to the 26 watts. But we'll just use solar units. And then we have solar radius. If you ever want to convert to how many kilometers that really is, or how many AU, you can do that on your own time. We're just going to use solar radii. How big is it in comparison to the sun? And our solar temperature, how hot is the sun's photosphere? 5,800 Kelvin. So a solar temperature. All right. So why can we use that simplified version? And I hope this doesn't cause more confusion. I hope this actually helps, because this is why it's oops. It's supposed to be why it's simplified. Making up words here, why it's simplified. There we go. So hopefully this will show you what's going on behind the curtain of this thinking proportionally, why we've been doing this all semester. I've shown this a couple of times already. But really, if I want to figure out the luminosity of a star, I could just apply the Stefan-Boltzmann's law. I could use the full equation to solve for things in like terms of watts for the luminosity of the star. And I would use this equation, 4 pi times the Stefan-Boltzmann constant times the physical radius of the star squared times the temperature in Kelvin to the 4th power. Radius would be in meters here. And that would give me the luminosity of the star in watts. I don't want to have to do that calculation all the time. I want to just compare it to something I know, the sun. So why don't we just divide that by the luminosity of the sun? And then that way, we're comparing the luminosity of the star compared to the sun. What is the luminosity of the star in solar luminosities? So it would be the same equation, 4 pi sigma r of the sun squared. Sorry, this circle with a dot means sun. I was being fancy whenever I made this one. And then temperature of the sun to the 4th power. Notice those stupid constants just go away. Don't need to memorize what pi is. Don't need to memorize what sigma is. Don't need to memorize what 4 is. Although you should know what 4 is. They cancel each other out, which leaves me with the radius of the star divided by the radius of the sun, number of solar radii, and then square that. The temperature of this star divided by the temperature of the sun, the number of solar temperatures the star has, raised to the 4th power. That gives us our luminosity radius temperature relationship in solar units. So hopefully that helps you see where this equation comes from and why when we use solar units, it becomes so simple. And then our practical version, because we measure the luminosity using telescopes and we measure the temperature from, say, its spectral class, its black body spectrum, a single spectral line, many ways to get the temperature. And that allows us to calculate the radius. Let's do it. Let's take some examples. Let's start with one of these giant stars, a red giant star, Aldebaran. It's a K5 star. So look, we're already integrating all this knowledge. We are listing its spectral class, K, O, B, A, F, G, K. This star is cooler than the sun. All right, so we have a K5 star. And what I can do is I can give you its temperature and luminosity. So it has a luminosity of 440 times that of the sun. Typically, we list the luminosities in solar luminosities. So it's 440 solar luminosities. Wow, that's a really, really luminous star. Well, it is a giant. It has a temperature, surface temperature of 3,900. It's quite cool. It's a K star, so it's cooler than our sun. It's at 3,900 Kelvin, which will give it a nice sort of orangey reddish hue. And if I'm going to actually use the radius luminosity temperature relationship, this is in Kelvin. I need to put it in solar units. It's not that bad. All I do is I take the temperature and divide it by the solar temperature. So I find out that the temperature of Aldebaran is 67% of that of the sun, 0.67 solar temperatures. Okay, so now I have all the information I need, the luminosity and solar luminosities, the temperature and solar temperatures. Now I can just use the luminosity radius temperature relationship to determine the radius of Aldebaran. And yes, it is that easy. So use the form where we have the radius equals the square root of the luminosity divided by the temperature squared. If I wanted to use this equation, I'm going to give it to you so you don't have to memorize it, other than you should be able to pick it out of a lineup. So you have 5 choices, pick out the right one. So just plug in the numbers. What is the luminosity in solar units? 440. I'm going to take the square root of that. Now I'm going to divide that by what is the temperature in solar temperatures? 0.67 squared. You can go ahead and calculate it. Might as well go ahead and do that for you, so you can believe me here. Give me a second. Deleting all my memory so you can cleanly see the answer. So the square root of 440 divided by 0.67 squared, I get 46.728. Where literally all I did was plug in the numbers and let my calculator tell me that that star has a radius of 46.7 times that of the sun. Holy crap, we just figured out how large this sun is, or this star is physically. It's about 50 times bigger than our sun. That is huge. It's a red giant. Oh, sorry. Man, there are a lot of typos in this one. I apologize for that. This is what happens when you make too many videos too rapidly. All right, so let's look at another extreme. Let's look at a white dwarf star. So if you look out, Sirius is the brightest star in the sky. It has a binary companion star, though, Sirius B, that's in orbit around it, which you can't see with the naked eye. You can see it with a telescope, but it's really, really hard to see because it has a really, really low luminosity. It has a luminosity of 0.3 solar luminosity, just 3% the natural brightness of the sun. It has a surface temperature of 25,000 Kelvin. That's a really, 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 really hot small star, or hot, not luminous star. So what is that temperature in solar temperatures? 25,000 divided by 5,800, 4.3 times hotter than the surface of the sun. Now we can just use our luminosity radius temperature relationship, and might as well go ahead and plug it in. If I showed you last time, I'll show you this time. So the radius of this star would be the square root of 0.3 0.03 divided by the temperature in solar temperature squared, 4.3 squared. And I get a really, really, really small number, 0.009 times that of the sun. About 1/100th the size of the sun. That's the size of Earth. This star, a white dwarf star, is technically not really a star. It doesn't have nuclear fusion happening in its core. It is the dead remnant of a star like our sun. What our sun will become after it goes through its death throes and dies. It'll end up as a white dwarf. But notice here we have a star that's about the size of the Earth, making it really, really small, truly a dwarf. But it's really, really hot, a temperature of 25,000 Kelvin. So it look pretty white and a little bit bluish to the eye, making this what we call a white dwarf star. Amazing that we can figure these things out. All right, so we can now determine the radius of stars, the sizes of the stars themselves. Another property, check. But let's take a moment before I end this video to really see how far we've already come. Because I know this feels like you've gotten a lot of information about the stars and you're drinking it from a fire hose. But let's take a step back and just appreciate what we've learned so far, because it's absolutely phenomenal to just take an inventory of what we've been able to do so far. We can determine the distances to the stars, and we do it using stellar parallax. We can determine the luminosity of the stars using the distance modulus and the magnitude system. We know the apparent brightness. We know the distance from stellar parallax. We can find out the absolute brightness. We can find out the luminosity. So there's our first stellar property. We know the luminosities of the stars, the energy production of stars. We can get the temperature of the stars in a variety of ways. We can use the color index, photometry, photometric measurements, or we can take a spectrum, a spectroscopy measurement, determine the spectral class. Both of those give us temperature. Or you can be really, really fancy about it and look at one of the individual lines, look at the width of the line, and determine the temperature that way. Well, we can determine the temperature of the star. That's two properties, luminosity and temperature. We can determine the composition of stars just by looking at their spectra. What spectral lines are there? Match them up with the spectra of the elements, and you've determined the composition of the stars. And now we can determine the radius, because we've already determined the luminosity and the temperature, and they all relate by Stefan-Boltzmann's law via the luminosity radius temperature relationship. That the radius, or the luminosity, I like it that way, is equal to the radius squared times the temperature to the fourth power, if everything's in solar units. So we've determined some pretty amazing things about the stars just from the light that we're receiving. The luminosity, a measure of how bright it is, how much energy it's producing, its temperature, which also tells us its color, the composition, what it's made out of, and its physical size. We've determined so many. And now that we have all of these properties that we can just measure, we can get from just a couple of measurements and some pretty, you might think complicated, but in the grand scheme of things, pretty simple calculations. With so many properties measured, now we can do some really powerful stuff. We can start comparing these properties to see how they connect to one another. And where there's a connection between these physical properties of the stars, there's some physics that's doing the connecting. And that'll allow us to really start probing into the natures of stars. And whenever we see these connections, what other things might they lead to? What might they lead us to discover? What other properties might we be able to find by using and leveraging all of these physical connections? So I wanted you to get an appreciation of just how everything we've been working towards is coming together in this unit on stars, this part on stars. I hope you've appreciated it, and I hope you liked learning about all of this. We're going to continue after the properties of the stars soon.